All right, for this portfolio, we have the first topic, topic number 5. For turbulent flow in a pipe, why is the flow near the wall of the pipe more laminar than the flow in the center? And this is essentially because turbulent flow has radial movement, which is what causes the turbulence and causes loss in energy because of the momentum transfer and friction loss. And near the wall, there's less of this radial movement just because there's less direction for the fluid to move in. Because in the center, it can move in any direction, but near the walls, it can only move toward the center. And so there is less turbulence near the wall compared to the center of the pipe. Now for question 2, you have a 20-meter hose and you need water to water some flowers that are 22 meters away, since it's a hot 35 degrees outside. Find the diameter you must restrict the flow to with your thumb in order for the water to flow and the minimum inlet pressure to achieve the flow. The hose has a diameter of 3 centimeters and a height of 1 meter off the ground and an inlet velocity of 1 meter per second, and your thumb on the end of the hose can be treated as a sudden contraction. So we're given the inner diameter of the hose, the length of the hose, the temperature outside, the velocity into the hose, and the height of the hose off the ground. Now, assuming we pull the hose completely taut, there will be no height change, and the length would be the full 20 meters, so we only need to get the water to go an extra 2 meters to get to go the full 22. We are told to find the exit diameter we need to restrict the flow to and the inlet pressure in order to overcome the friction loss for that diameter and that sudden contraction as stated in the problem. And so we have to assume alpha is 1, outlet pressure is atmospheric pressure because it's venting to the atmosphere. We have our properties. And the first thing we have to do is find the exit velocity, which we get by doing a physics 1 calculation for delta x, velocity acceleration, and we get 4.43 meters per second. Via that, we can find the exit area by the ratio of the velocities. So we have the outlet velocity and the inlet velocity, as well as the inlet area. And we get an exit area, or a exit diameter of 0.0425 meters. From that, we can get the Reynolds number, confirm that it is laminar, so we can then calculate friction factor and the KL from the sudden contraction. We get that to be 5.2, the head loss from the friction factor to be 5.28 meters. Plug that into a Bernoulli's balance, and we get an inlet pressure necessary as 161.74 kPa. For topic number 6, why will the ethanol and water have a different MPSH required for the same pump and flow conditions? And this is essentially because NPSH is based on vapor pressure, and different liquids such as ethanol and water will have a different vapor pressure, which will affect the NPSH required as shown by this equation here. For your skydiving, you want to pull your parachute at the last possible second. It is 25 degrees outside and you weigh 100 kilograms with all the skydiving equipment, and your parachute has a diameter of 10 meters. Find the initial terminal velocity and height you need to, and the subsequent height you need to pull the parachute to decelerate to your new terminal velocity. Neglect the human drag after the parachute is opened and utilize average velocity to calculate the drag force of the parachute. Also, assuming instantaneous deployment of the parachute, and neglect the large jerk force that would create that this would create in the survivability calculation. And so essentially, since we're assuming that the parachute is instantly deploying and that we use the average velocity to calculate the drag force, there's going to be an extremely high acceleration value for this problem. And so we're given the diameter of the parachute, the temperature, and your mass, and we're told to find the initial terminal velocity and the height necessary to pull the parachute in order to fully decelerate to the second terminal velocity after you pull the parachute. We assume the drag force can be approximated by the average velocity. We're told to neglect the human drag force, and the diameter value for a human is 1 meter. Now we're given our properties, CDA, coefficient of drag. So first thing we find is the initial terminal velocity, which we get by doing rho v squared of the coefficient of drag of a person. And we get a terminal velocity of 44.4 meters per second, which does make sense. Then we get our Reynolds value, and we confirm that it is turbulent flow. And so then we get the second terminal velocity from the same equation. We get the second terminal velocity to be 4.2 meters per second, which does make sense. That is a survivable crash velocity. And from there, we again confirm that this is turbulent. And from there, we calculate the V average, the drag force from that velocity average, and the acceleration from that drag force, which we find to be 344 meters per second squared, which is obviously unreasonable, but according to our assumptions that the drag force can be approximated by average velocity and an instantaneous deployment of the parachute, this does make sense, since in real life, a parachute would not instantly deploy, and the drag force would decrease with decreasing velocity. With this acceleration, we then get a height of 2.84 meters. For topic number 7, why does the density of fluid not affect flow through porous material when the flow is laminar? And this is essentially because for flow, there is the inertial term and the viscous term losses. And for Stokes flow, which is laminar flow through a porous material, the initial term, or the speed of the fluid, is extremely low, and so the inertial term is extremely small when compared to the viscous term. And since the density only affects the inertial term, then the density does not matter as much as the viscous term, and therefore does not affect the flow nearly as much as normal laminar flow. Now for the calculation question, assume you want to beat Andy Dwyer's superstraw record, which is 3 meters, as pictured below, by drinking through a longer straw, but you decide to drink boba water, where the diameter of boba particles approaches the diameter of the straw, which is 1 centimeter. Assume they are equal, but the liquid can still get by. Assume the worst case scenario happens and the boba gets stuck along the entire length of the straw. What is the minimum vacuum pressure necessary to drink the liquid if you were to drink horizontally from the cup, no change in height, and no pressure from the liquid in the cup? It is 20 degrees outside, and you have to drink 32 ounces, 0.01 cubic meters of fluid in 12 hours in order to break the record. And so we're given the length of the straw, we're given the diameter of the particles as well as the diameter of the straw, and we're given the time necessary to drink the fluid and the volume necessary to drink in that time. And we're told to find the pressure vacuum, which we're going to have to find the pressure of the mouth max in order to minimize the vacuum pressure. We're told delta H is equal to 0, liquid is pure water, boba are perfectly spherical, and the velocity of the liquid is constant over the 12 hours. Here are our properties. First we have to find the superficial velocity, and then we can get the void fraction based on the ratio of a volume of a sphere to a volume of a cylinder. Plug that into Reynolds, which we do get as being laminar flow. Plug that into the laminar flow equation to then get a P2 max of 101,309 pascals, which is a vacuum pressure of 15.9 pascals. Now for the last topic, why is the Mach number of a converging nozzle limited to 1 or less? Now this is essentially because the pressure and temperature coincide with the maximum mass flow rate, which can be shown as a function here. And if we differentiate it with respect to Mach number, or the speed of the liquid, we get a Mach number of 1 if we set the differentiation to be 0, which is what it would be at the maximum value, because at the maximum value the mass flow rate would not be changing. And so we get a maximum Mach number of 1 from that. This also makes sense because pressure can only move through a liquid or gas at a rate of the the speed of sound. And since force travels through a gas as pressure, they would not be able to accelerate anymore because force would not be able to move through the gas faster than the gas itself. Now for our final question, find the inlet temperature and pressure necessary to accelerate air to the speed of light in a converging nozzle that vents to the atmosphere. Assume gas constants are constant at their value for 25 degrees Celsius. Now this is necessary because at the extremely high temperatures and pressures that this problem is going to be calculated at, the gas constants actually change from what they are at like the normal 25 degrees Celsius and are way farther apart. And the K value will also change since the values get closer and closer as the temperature increases. So then we know the exit velocity, which is equal to the speed of light. We're told to find the inlet temperature and pressure. We can assume steady state. Mach number at the exit is 1, since we're at the speed of light. Inlet velocity is negligible, and Rk is constant with change in temperature. From that, we calculate the temperature exit from our inlet velocity in C, and then from that, we are able to get stagnation temperature and stagnation pressure to then calculate the inlet from those stagnation. And because the inlet velocity is 0 and T0 and Ti are equal, our inlet conditions are equal to the stagnation conditions.